Okay, fantastic. Um, Welcome, everyone. Thank you for joining us for today's SLAM seminar. Uh, we are very excited to invite and introduce SJ Kole, who will be giving our SLAM talk today. SJ completed her PhD in condensed matter physics at the Indian Institute of Science in Bangalore with Chiral and also worked with Gareth Alexander at the University of Warwick. She followed this with a stint as a Newton-Simons Fellow at the University of Cambridge, working with a group of Mike Cates. Her research, and currently, if I remember correctly, she is now a postdoc with Juan de Pablo's group at the University of Chicago, working on various problems in liquid crystal physics and active matter. Her research lies broadly in non-equilibrium statistical physics and soft matter, with a particular focus on hydrodynamic theories of ordered phases. And she is going to tell us about broken symmetries and activity, and sort of an interplay of large number of very exciting topics in elasticity, ordered elasticity, and chiral crystallites. So thank you again, SJ, and take it away.
Thank you. Thank you, Suraj. Thank you for the kind introduction. And thanks to the organizers for this opportunity to sort of talk about my research work. And thank you all for joining, to hear my research work. So what I thought I would talk today is sort of a collection of works, all connected with the theme of broken symmetry hydrodynamics and out of equilibrium physics. And so how I would do this is so how I would do this is start by setting up the stage. So I'll make precise with, what all I mean by activity, chirality, broken symmetry states. And once the stage is set, then I'll, go on to broken symmetry phases. So translationally ordered systems, or, within which I'll mostly focus on something called as layered phases, but I'll quickly browse through the results that I have on columnar phases, 3D solids, and so on. And then move on to sort of interplay of multiple broken symmetries in Quincke roller experiments. And so this is the sort of framework or overview in which I'll sort of talk today. And so to begin, the first part of the first half of the talk would essentially involve wet active matter, which is, as by now everyone, I guess, if not aware, is active matter is a collection of self-driven particles. And now in the in sort of the projects of work that I'll be talking about, I'll be focusing on self-driven particles in a fluid. And so the way they move, if they are polar, if they break 4-hour symmetry, is by applying stresses in the fluid. So they push against fluid and then they propel. And broadly, the way, so you can have two classes of swimmers, extensile or contractile, which depends on how the swimmer sort of exerts, forces or creates flow fields in the suspension, in the fluid medium. And this will be relevant to what I talk next, but essentially what we need from this slide is that there are two kinds of swimmers, and that are distinguished based on what kind of stresses they induce in the fluid medium, and that is whether they pull along their body axis or they push fluid along their body axis. So just so that I, go over what's been done in the past and what I am actually filling in here is people have focused since 2002 for the first time when Sriram, my PhD advisor, worked on active pneumatics, orientationally ordered phases. And so what you see there is that activity within pneumatic phases sort of leads to generalized instabilities, either for contractile swimmers or extensile swimmers, depending on what stresses you exert. The corresponding modes, like splay modes or the bend modes, get unstable. And you get this generalized instability, which is that you can never have a long-ranged ordered active pneumatic system, depending on what form of activity that you have. And so this was later on experimentally, I think recently in 2019, that it was verified um, for the active pneumatic instability. So the question I ask here is that for an active ordered pneumatic, which is a system that breaks rotational symmetry, so it's ordered along a specific direction, what happens if you have systems that break translational symmetry, which will, endow you with elastic modes, like linear, like solid, like elasticity. And so how does the Simha Ramaswamy instability or the generalized pneumatic, active pneumatic instability more, change with translational order? And so I look at this question in different variety of phases with coupling that have both translational order and fluid-like order. And so as I've just mentioned, a pneumatic that breaks orientational symmetry. And so while a solid which breaks, translational symmetry or has finite position correlations. So the, 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 the place where you can have, both a combination of liquid-like and solid-like properties is essentially liquid crystals. So they give you a rich, sort of phase space to explore. And so the most of the talk, the initial part of talk, will involve different liquid crystalline phases which have both translational order and fluid-like responses. And the second theme that will be universal throughout my talk is chirality. And so just to set the stage, what we mean by chirality is what Lord Kelvin defined for us. That is, an object is said to be chiral if it cannot be superimposed onto its mirror image through rigid motions. So it's handedness. And for the purposes of the talk, the way I will objectively use chiralities through cross products, our usual intuition, and so on and so forth. So why do we care about chiral active matter? Across biological systems and artificially realized systems, you see, chiral organization starting from subcellular um, chiral organization during embryogenesis and the chiral flows that get established, or the cholesteric phase. I'll talk about the cholesteric phase, but that gets formed by DNA helices in dinoflagellates, or at the tissue level where cells undergo chiral transitions, or in artificial systems that in the group of Ajay Sood, where you have these artificial dimers that show variety of rich chiral phenomenon, chiral active phenomenon. And so moving to the first part of the story, so two materials, both layered, one smectic, the other is cholesteric. What I mean by smectic, or what people mean by smectic, is essentially a liquid crystal, a material that breaks translational symmetry along one direction and has fluid-like correlations in the other two directions. So you have, as you can think of this material as though it's layers of mass density wave that at each of these horizontal lines, you have a peak in the mass density, and then it oscillates as you go along the direction of the translational, along the direction that you break translational symmetry. And so you can have a Fourier decomposition for that. I'll not get into the details of it, but eventually it will be necessary to understand why I wish to think of these systems not in the Q framework, the usual Q tensor framework, but in terms of density waves. And just to remind us that these layered materials break both rotational and translational symmetry, but the elasticity and the hydrodynamics is just given in terms of one Goldstone mode. That's the displacement field. So just like a solid, you have a displacement field that describes the elasticity. In this case, it's a 1D solid and the other two directions are fluid-like. You have just one displacement field that governs the elasticity completely. Cholesterics, the difference is that I've been talking about these long rod molecules. If they're chiral, then instead of, sort of aligning in like an ordered nematic or a smectic, one of the phases that they exhibit is what is called cholesteric phase, where these long molecules, they want to, sort of pack. And the best way to do that is through a helical modulation. And again, I would look at these cholesteric materials as though they are layered phases. The way I would call them as layered is you say you are at a point here, that's along the where I have shown the arrow. And so you say that's your one layer. Then the next layer is going to be half the pitch, and so on and so forth. So you'll get, where once you choose a plane, then the next time the director aligns along the same direction, that's your plane. So you think of it as layers. So I'll insist a Q-tensor description, and I'll talk about it later. Quickly, as I said before, the elasticity is just in terms of the displacement field of the layers. It's basically given by a compression modulus. That is, if you were to compress on the system like a solid, you would have a response along the solid direction and a higher order bend modulus. But there's no, tilt modulus. That is, there's no response along the fluid directions because of rotational invariance. But the only thing that we need to remember about this is that in equilibrium systems, you do not get a response along the fluid directions in the elastic. At the orders of bend modulus, you don't get a response. And to quickly go through earlier results very quickly, what happens, what's the interesting physics that you see in these systems is that if you were to say compress on these systems, they're trying to maintain the layer spacing. And so because there is an external stress on these materials, the way they do so is by buckling, undergoing a buckling transition, and you get these Helfrich-Hero instabilities that are well studied. And the second point is that at thermal equilibrium, the long wavelength elasticity and hydrodynamics for smectics, which is an achiral material, and cholesterics, which is a chiral material, that's the same. So it's blind to chirality, the equilibrium physics. So as I said, I would do the active chiral version of layered materials. And the way it's done is in the spirit of field theoretic formulations, first started by Halperin and Hohenberg long back, and then for active systems done majorly by a lot of it is done by the group of Mike Cates. And so what you do is the chiral extension to the active model H, which we call active model H star for chirality, which is essentially coupling two fields. One is the density field, and that's where, my earlier point on I wish to see these layered materials as density decomposition or density modulations comes here. And that is coupled to an external momentum field. The guiding principles to construct, such a field theory is symmetries and conservation laws, and that's it. So you have a conserved density field, so it's a conservation law. It follows a conservation law. It's advected by a velocity field, so you get the time gradients in time derivatives of psi of the density field are advected by a fluid field, and it responds to currents in the gradients by the gradients of the density field. So that's essentially how the density sector evolves. The fluid sector, the momentum sector, evolves through, we'll assume a Stokesian approximation. So essentially, the Stokes drag is balanced by stresses. And so here, because I'll be talking about active and chiral materials, there are two sorts of stresses that are allowed. One that just breaks time reversal symmetry, the other one that breaks both time reversal symmetry and parity symmetry. And so the blue bit is the achiral bit that just breaks time reversal symmetry, while the sigma c, the red bit, is that breaks both time reversal symmetry and inversion symmetry. So that's the chiral bit. And so uh, for people who like to think of it in terms of microscopic modeling, what this means is that the blue bit comes from coarse graining force dipoles, and the chiral active stress comes from coarse graining torque dipoles. And the form is written on basis of symmetry arguments. The blue one is, of course, well-known active model edge stress or the active pneumatic stress. If you assume grad psi is like a pneumatic and director field. And the chiral active stress, as you see, looks a little complicated, but essentially it's a curl. It's the lowest order curl that gives you a non-zero contribution, a non-zero force in the velocity equation. That comes out, and so what you do is you assume a certain density modulation for the layered phases via the Fourier transform that I talked about before, and plug that in these stress terms, calculate the force and calculate the velocity field, and see what the mode structure is, what happens to the materials, and so on and so forth. You have a
Isha,
question? Yeah.
can I ask a quick
Yes,
question?
please. Yes, please. For sure.
So the cartoon you have over here shows a sort of
Yes.
Hawk dipole along the with the dipole axis aligned with the long axis of the order.
Mm-hmm.
Uh, can you have other situations? Can you have once is it possible or will that is it possible to have a chirality axis
Different from the long body
different from
axis.
that
Yeah.
of the order, and what will that look like? Is that included within this framework, or is that a separate characterization of a different kind of an active stress?
Yeah, that's a good question. So, I think that is, of course, allowed. You can always have, the inversion symmetry being broken along. Say, suppose if you're looking at 2D
Hmm.
being broken along a certain, like maybe biaxiality or something, while it having a principal axis along other direction,
Hmm.
if that's what you're trying to imply.
Yes,
So,
yes.
and that's of course there. However, the terms that I have here actually do not even need orientational order. What they need is the concentration field and the fact that they're chiral. So,
Yeah, sure, sure, sure. Yeah, but the
Mhm.
concentration is varying in along one axis,
Sure.
which is the sort of pitch axis, if you want.
Yes.
And what I was asking was, can you have a
Okay.
situation where now, in addition, the
Mhm.
driving has a separate
Yeah.
axis along which it acts?
Yeah, yeah, for sure. Yeah, if you have a directionality in the system, then of course you allow for lower order terms, and then that can, of course, do some interesting,
Okay.
yeah, for sure. Yeah.
Are there other situations that one can think about, which is, for instance, toroidal dipoles? So then they still have, they don't pick out, they only have one axis. They still they can be aligned with the pitch axis, but then
Hmm.
the chirality is now not twisting along the long axis, but is sort of, there's a circulating, if you want, like a current. Um,
Hmm.
uh, it's sort of higher order in a sense, multipoles that one can maybe envision. And I wonder if there are um,
Yeah,
Are there other organizations of torque dipoles, uh, when what they, and what they would look like in some coarse-grained stress?
yeah, for sure. Yeah, that's an interesting point.
Because
Off
I'm
the
thinking
top
of
of
like
my
vortex rings. I'm thinking of if you're thinking of vortex rings that can have some circulation, um,
Mhm.
but they have a single axis. They have because the ring has a
Yeah,
one normal, and I was just wondering if a collection of vortex rings,
could do something.
what would be the effective stress that would be generated by that?
If a collection of vortex rings sort of breaks, at the macroscopic level, if breaks isotropy,
Hmm.
then I see that it leads to, um, other stresses, other forms. But if not, then I would assume that, that the local, anisotropy to say, if
Hmm.
does not survive on the long range
Sure.
scales, I think this is what it should
Okay.
go
Okay.
to. Yeah.
All right. Thank you.
Thank you. Yeah, sure. I mean, yeah, I would appreciate questions rather than it being a monologue. Um, very quickly, I'll just not get into the messy details of the calculation, but just highlighting the crucial important bits here. That is, as I've said, I'll employ a density field description for this. And so you start with a Swift-Hohenberg energy, which essentially means that you have a free energy functional that when you minimize gives you a state that is periodic along, a certain direction. And that periodicity is set by the pitch QS that you see here, and the fact that it comes with a negative sign with a higher order stabilizing uh, term, you get a periodically modulated state when alpha is less than 0. And so you use this generic formalism, plug in the um, density wave in Fourier decomposition that I mentioned before, you obtain the elasticity. So you see that indeed the nonlinear elasticity lacks a tilt modulus at the order of compression modulus in smectics in layered phases in general. And so what happens, like, not going into the details of the calculation, what comes out of it is of when the dust settles down is that the bare activity, the term that just breaks time reversal symmetry, what you get out of that is a tilt modulus to say. So you get a response along the fluid direction at the same orders as the compression modulus along the solid direction. And now you can think that there's nothing that's competing against it in the passive case, in the passive response. So depending on what sign the activity is, you should, make your material. You should, the material is expected to undergo generic instability without any threshold. And so that happens. And so for extensile systems, the tilt modulus is stabilizing, but for contractile systems, it is destabilizing without any threshold. So it's generically unstable because of usual bare activity, uh, the active bit. So this is what happens. So as I said before, that if you had a passive system, you apply external stresses to it, they undergo these buckling instability. But if you have um, a an active version of these lamellar phases, you don't need external stresses. They are like, as soon as you have contractile activity, they are like, self-driven, and they undergo these buckling instabilities. Helfrich Hilo. So what more comes out of this is that you have a analogy between the externally stressed passive uh, layered state and an active layered state. not just in terms of the instability that we see, but also in terms of the exact, analogy, in the sense exact mapping between the two states. So you can always compensate the active stress via external stresses. The physics, the phenomenology remains, exactly same. And so that happens for multiple translationally ordered states, which is interesting. Um, that you can sort of have an effective free energy like description for these active systems. What happens with the chiral activity? You get vortices. So once you have the undulated state, the chiral activity decorates it, with vortices, and it's an higher order effect, so it does not break the mode structure at the instability that I described to you. And so with these two inputs, what you get is a vortex lattice state, which is a square lattice. This comes out from the exact mapping that I showed you before. So the instability is, you know what state it gets into. And then the chiral activity, which is at higher orders and so does not affect the mode structure, just decorates it with these vortices on top of the already established undulated state, and you get the vortex lattice state, which is linearly stable. Um, and you get an antiferromagnetic alignment um, of the vortices. So I'll not get into the other works that came out of this, but just go through them quickly, and move on to the other phases. But so what we get out of this exercise, is that you have a field theoretic formulation for the for chiral active systems, the active model H star. Then the cute results, or uh, fascinating results to us, is that the active cholesteric is not the same as active smectic, which in the passive case, they had the same elasticity. And what you also realize is that systems with screw symmetry versus chiral systems that do not have screw symmetry. So cholesterics have screw symmetry, but smectics, say A star, they are layered phases. You have chiral inclusions, but they do not have screw symmetry. They also are distinct when they are active. Due to a chiral instability because of the rotation translational coupling. So the fact that in cholesterics you rotate, that amounts to a translation along the pitch axis. This leads to interesting couplings, and you get interesting chiral active instabilities. More of it is in this archive preprint. And that you get these vortex lattice phases, which you can essentially switch on or off by uniaxial stresses. And so you can engineer sort of, at least the linear stability, these vortex lattice, spontaneous vortex lattice states, which comes out essentially because of the interplay of activity geometry, broken symmetry physics. All right, so if there's anything on this, I am happy to take up. If not, then I can move on to the next ones.
So
Yes.
you discussed a chiral contribution to the activity. Are
Yes.
you assuming at the same time a chiral contribution to the passive free energy?
Yeah, that's a good question. So the chiral contribution to passive free energy, or the elasticity, is at way higher orders
Hmm.
than the responses that you would be interested in, like compression modulus or the tilt modulus. So indeed, there exists chiral responses, but they are at way higher orders in gradients.
Okay, so the cholesteric layering is expressed here as a smectic layering, but this free energy doesn't know whether it's a left-handed or right-handed cholesteric. Is that the idea?
Um, so the point is that you can include, and it's not here on this slide, but it's in the paper that when you include the chiral term with a pitch, that's at way higher orders in gradients. And at, the mode structure that we are analyzing, where all of this comes out, that bit is irrelevant. So that's the point. It's at the leading orders that physics does not affect. But of course, for the fact that if you were to, send in light waves, electromagnetic radiation, that would see the fact that it's a chiral object. So yeah, so you have chiral responses, but not at the leading orders in elasticity and hydrodynamics. That's my point.
Okay, thank you.
Thank you.
Maybe along the same veins and building on the response you just gave us, Jay,
Yes.
is there an active analog of lemma rotation? Or
Yeah, I've thought about it.
Can you unwind and change the pitch?
That's interesting, and I think it should be there, but I've not encountered anything as yet. But yeah, I had thought about this before, that if you could sort of unwind and zip open the cholesteric or any chiral structure. I don't see why that is forbidden, but I don't know of an example.
Would you have a situation where as you unwind, because within a pitch,
Yes.
well, if the pitch becomes very long, then locally you're just a regular pneumatic. You
Mm-hmm.
don't know of chirality, you don't know that you're twisted, and then the pneumatic should be unstable. So is there something wherein as you unwind, you get like that you get actually interrupted, that you start dissolving beyond some threshold pitch?
There are passive analogs of, like this unzipping, zipping out the sort of twisting.
Yes, I agree. But if it's
Yeah, yeah.
active,
Then possibly the fact that you have a certain length scale that you're always competing against, it's possible. But I need to see a calculation to say that. Yeah.
okay,
Yeah.
okay. Thank you.
Thank you. Right. So moving on to the other translationally ordered system that I want to talk about is the columnar phase. So columnar phase is a dual to the layered phase, metric phase that I was talking about. Here you have 2D elasticity and one-dimensional along the column direction fluid like phases. Um, uh, so first observed at the Raman Institute back in 77, Chandrasekhar and others. So here you have these essentially what it gives us, lends us, is with 2D Lame elasticity and a column, higher order column bending modulus. Here again, what you do is assume a 2D modulation. So the wave vectors come from a 2D reciprocal lattice, and I'll focus on columns that are polar. So that is along the Z direction, they break polar asymmetry. So they are directional along the column axis. What happens with this is that the usual activity gives something similar, that it leads to buckling instability of undulational instability of columns. So the activity gives you a column tension, and depending on what sign of activity you have, it can either go stable or unstable. What happens to the chiral piece is that it gives you the odd elasticity, the 2D odd elasticity in a 3D medium. So 2D odd elasticity is widely studied, and here in Vincenzo's article. And so the bit is that because of the fact that these are polar objects and chiral, so you have a 2D solid like material and a third dimension which is fluid. It cannot be absorbed into pressure, and and it has consequences because of the fact that it couples with a fluid direction. And so what it leads to is an interesting wave-like response plasma on oscillations, where the mode structure is independent of the wave number. So there is like, even at the q going to 0 limit, you have a singular bit, you have a response, and it is directional. So depending on the angle of propagation with respect to the column axis, you either have these oscillations, plasma-like oscillations, or they die down. So they die along the column axis and in the plane, and they are, singular. So they have a piece even in the q going to 0 limit. And so this comes out of the odd elasticity. So odd elasticity realized in liquid crystalline settings, the 2D odd elasticity, which leads to something, that can be experimentally mapped, has consequences. And so that's there in this article. And I will maybe quickly just sort of highlight that if you work out the same for 3D solids in an isotropic medium, possibly relevant for biological systems, they show generic instabilities due to chiral activity. And so I'll not get into that, and maybe perhaps move to the second half of it, unless there are questions.
Well, I am wondering for all of these phases, what is the experimental outlook, right? Theory has gotten a bit ahead of experiment again, right? Which worked out well for pneumatics, but are there possibilities on the horizon?
Mm-hmm. So for the smectics or layered phases, or even for these columnar materials, what you can, the first step that you can think of is using passive phases with bacterial inclusions, with active inclusions, or external feeds, and so on and so forth. But what we were able to sort of push through for the article is potential relevance to axons, because axon bundles also, are columnar. and may have, the fact that this ringing effects are there based on just symmetry arguments, may have some relevance. And so that's the grounded answer that I can give at this point.
Okay, and any for smectics and cholesterics?
Yes, for layers, as I said, like, you can start with the cholesteric and have bacterial inclusions.
Yes, okay.
And there are some experiments where Oleg Lavrentovich, where they, I think Oleg or Ivan, they have these cholesteric phases where they have, inclusions, and they activate it, and sort of, it shows similar structures, but like it needs more investigation, of course. Yeah. That was the last time. Yeah. Yeah. All right. Thank you. And so now what I'll move on to is, so to switch gears here. I'll talk about multiple broken symmetries and coupling between them, and what interesting physics that can come out of this. So these are Quincke roller experiments from the group of Paddy Royal, and so who's now at ESPCI. What I would show here essentially is that if you have multiple broken symmetries and they are coupled non-reciprocally, they lead to interesting novel chiral phases, and that you can use this broad framework, which we're just beginning to develop, as as a proxy interaction between multiple broken symmetries, as a proxy to control active systems. So very quickly, Quincke roller. So I'll not be looking at the the individual particle level description. I will be doing what I am trained to do, is the hydrodynamics and looking at collections. But just so that we know what these colloids are, you have these confined colloids. You have an external applied DC field that leads to polarization and if you keep increasing your electric field beyond a critical threshold EQ, these colloids start rolling, and that you get, active colloids, self-propelled colloids. So what difference or what Paddy does differently is the following, that he's able to stabilize these, chemically stabilize these colloids so that below the critical threshold EQ, when they start sort of self-propelling, they form a hexatic phase, hexatic order. These particles, these colloids, arrange themselves in hexatic order. And as you keep increasing your EQ, once you hit the threshold, beyond that, the self-propulsion actuates, and then you get interesting, phases and interaction between clusters and so on and so forth. So this is what I'll be modeling here. So as I said, so you have hexatic ordering due to attractive interactions, and above a critical threshold, you see self-propulsion, and then you see, clusters of a certain size that depend on an external field, moving either clockwise or counterclockwise. Both are seen. So to understand this, I'll take a step back, and that's so what I'm looking at the experiments and just looking for essential ingredients, and now trying to construct a field theory that's relevant to these systems, and then later on I'll connect to these experiments. But what you see is that you have two broken symmetries, at least in the sense that you would want to view it. So you have a hexatic order and you have self-propulsion. And so the hexatic order comes from the attractive potential. And in the Euler representation, that's what I'll be using. You have, a vectorial order, that's phi, polar order. You have hexatic order, that's the psi 6, or the the six-fold symmetric order. And that's also written in the six-fold symmetric Euler representation. The phi naughts and psi naughts talk about the amplitude of the mode, the order, and the phi, angle phi, small phi, and theta talk about the polar angle and hexatic bond angle, which is really the, sort of a combination of these actually is the slow mode. And so you have these two fields. You would write the rotationally invariant framework for these, for an interaction between these two broken symmetries. And again, you do so by symmetry allowed active terms. The essential bit is that because these systems are active because of the external field, electric field, and you can allow for non-reciprocal responses. And non-reciprocal responses in the same fashion as A and B having some sort of symmetry, asymmetry, but in specifically precisely what I mean for my the field theory is that the theta or the phi field will explicitly the equations of motion for these two will explicitly break on Saga symmetry, and that's how I employ activity in the field theory. And what comes out of this is that you can think if you were to have an equilibrium system which was studied back in 1980s by first by David Nelson, I got that wrong, sorry, by David Nelson, and recently by Tom Lubensky, wherein you have equilibrium phases. In the case of David's paper, it was a hexatic phase coupled to tilt degrees of freedom. And so these coupled n-atic systems that you get, it's easy to see that if there's an equilibrium version to this, the polarization would go and align along one of the hexatic easy axes. And while what happens with active is what I'll tell you about now. So you just have one Goldstone mode, even though you have two fields, you just have one, because the polarization just goes and aligns along the, once is fixed to the hexatic easy axis, and is slaved. And so what equations of motion that you get for the active case is the following, that you see that when the system is active, the fact that your polarization wants to go and align along one of the hexatic axis is not the only allowed uh, fixed point. You get another one wherein the polarization can have a misalignment with the hexatic, so there can be an angle difference between the two fields. And correspondingly, what it implies is that the mode, the Goldstone mode, which is the sum of alpha and sum of these two angles, starts rotating spontaneously. So you get these rotating clusters wherein the polar order and hexatic order have misalignment, but both of them start sort of rotating. And so you get these sort of macroscopic phases in these Quincke roller experiments wherein, because of the degeneracy of the solution, that you allow for both clockwise and anti-clockwise rotating clusters that are linearly stable, you get these chiral responses of clusters. What we did after this is looked at, sorry.
Can I ask a
Yes,
clarifying
please.
question? So you're only looking at coupled polarization in hexatic order,
Mm,
but you also say that these were crystallites. What
yes.
about elasticity?
So that's of course there. So you can have hexatic rigidity and also the polar orientational order, even that. But all of that, what I'm describing here is the mean field limit.
No, what I'm asking is shear rigidity.
The shear rigidity, um, I think essentially these are hexatic organizations, if you like, and that's the relevant response here. I mean, thinking of them as like crystals might be misleading. That's the reason why I call it crystallites.
Okay.
Yeah.
But is that given that there are experiments, is it possible to calculate the extent of shear deformations? Because shear will also couple to the hexatic, right? Even
Yes, for
kinematically,
sure, for sure.
um,
Yeah.
and shear rate. And so, do you have a sense from the experiments at the very least what the scale is, and can you uh, assess how important shear modes versus hexatic distortions, which one wins and which is more important? Maybe there's a size dependence.
Yeah, that's true. Yeah, indeed. Yeah. I don't know as the top of my head. The experiments were essentially measured for the hexatic responses, but you are indeed right. The fact that if they keep growing,
Yeah.
then these hydrodynamic effects are indeed going to shear them off, and that can, yeah, you sure, for sure, yeah. But I don't know the precise details of those measurements. Yeah.
Okay. And this video that you have in the
Yes.
bottom right, is that a simulation or the experiment?
No, that's the experiment. Yes,
The
it's just
experiment.
yeah.
And the colors, what are we seeing?
So yeah, so the red is essentially, if you want vacuum, I mean, it's of course fluid, but for the purpose of theory. And what you see here are these, they cannot be resolved, but these are like clusters of these Quincke rollers, wherein, individual particles are of course not resolved, but they're like, yeah. So
And
what you're seeing is the boundary of a cluster.
in the flashing, that the color sort of flashing, what is that?
Oh, that's just microscopy. Yeah, I don't think there's
Okay,
any.
that's just an artifact.
Yeah,
It's not
yeah.
telling us something about order or something. Okay.
Right. So, anything else? If any other question? Right. So what we did next with this is see how, really this amounts to in the experiment. What it amounts to in the experiments is whether do we get the rigid rotation and how that scales with, the systems, these cluster sizes, and so on and so forth. So this is analyzed at the cluster level, at a rotating cluster level, and you see a rigid body rotation, and then there is, a periphery wherein you have a fluid like response. It sorts of decays down, and then in a jammed system wherein the field theory is exactly relevant because I've not included a density field, is where you are able to sort of pick out the angle difference that exists in these systems, and that indeed these systems have constant angle difference, and when they have enough, if they are not jammed, they sort of lead to rotating clusters. So that's about it. And so the first part of the work was done in collaboration with Sriram, Gareth, and Ananyo, and the later one with Paddy and Tani, and my funding agencies over the years. And thank you so much for your attention. And of course, I would welcome any questions. Yeah, thank you.
Thank you so much, Esther, for a fantastic talk.
Thank you.
Okay, we have some time for questions. Please feel free to unmute and ask, or if you want to raise hands, then that's fine.
Can I ask a
Yes,
question?
great. Go
Sorry.
ahead, Jane.
Oh, yeah, going back to the experimental figure that you had there. So I was wondering, like, there are parts where it seems that instead of rotating, the smaller parts tend to not rotate. Could you comment on that?
Yeah, sure. Thank you so much, for that question. So, yes, indeed, there are, there are regions which are translating and not rotating. And the fact is because, we measured the hexatic order in these is low. So you don't really have hexatic order. You just have, the fact that these are, moving together is causes them, this requires the transition, if you like, the non-reciprocal transition requires the fact that you need two coupled broken symmetries. So those ones do not have hexatic order, and thus they do not show these rotations, active rotations.
Oh, okay. But I was wondering because these seem smaller. Is there a critical size at which the rollers exhibit the hexatic, or is that not related at all?
That is a good point. I Yes, indeed. So like the cluster size is dependent on the external field, the Peclet number, and so on and so forth. But I think what you're trying to ask is, do smaller clusters tend to be less hexatic?
Yes. Yeah.
That is, of course, not coming from the fact that you started with an attractive potential. That's coming because of what the local conditions are, and I think that's where what Suraj is mentioning, perhaps the fluid order, where you shear them and you break down the hexatic order and so forth. And so that physics is, in my opinion, is not at the order. It's not set by the potential to say the WCA potential is not going to worry about how big and small they are. Yeah.
Oh, thank you.
Thank you.
More questions?
So coming back to the question about experimental realizations, I'm just curious if you've talked with Zvonimir Dojic or Guillaume Duclos about the FD virus stabilized microtubule system.
Mm-hmm. I have not, but yeah, I know about those experiments. Yeah. Thank you. Yeah.
Yeah, because those are cholesterics, which is not deeply relevant in a first paper about them, but that doesn't mean the twist is not there.
Mm-hmm.
And I guess a related question is, do you expect the sign of the chiral stress term to be related to the handedness of the equilibrium material, or is it a totally independent parameter?
That's a very interesting question, and I didn't talk about that in here, but It's need not be. I mean, you the microscopic mechanism wherein the chiral activity is stemming from need not be coupled to, the fact that they want to twist in a certain fashion. So nothing dictates that they have to follow each other. And in fact, interesting things happen when they don't follow each other, wherein, your twist is one way, but the chiral activity is the other way, then you get instabilities of interesting sorts. Yeah. Yeah.
Yiren?
Yeah, I have a possibly elementary question because I'm not liquid crystals is not my field. So I know that in like 1 and 2 dimensions you can't have long range positional order, but in liquid crystals it's a 3-dimensional system, but long range order in only 1 or 2 dimensions. So like why is that possible while the other isn't? Like why?
Yeah. So that's an interesting question. So what you have is essentially quasi-long range order anyway. Um, um,
Oh,
and
okay.
and you also need to think
Even
about,
in the smectics?
and what you need to also think about is hydrodynamics. So, the correlations will, so what you are just thinking about is, the elasticity, the fact that it has, a certain form and there is noise and, uh, depending on the uh, instability criterion, depending on the dimensionality, you would either, get it or not get it. And the point about even in eclectics, yes, because you get these interesting singular structures that break the order. Yes, so that's there. It's always,
But but you can have these spectic and columnar in equilibrium
yeah,
systems, right?
yeah.
You don't need to think about hydrodynamics, is that right?
No, hydrodynamics, even equilibrium has hydrodynamics. The fact that they are coupled to a fluid medium, you will always have hydrodynamics. And so you can also look at the hydrodynamic correlations in the usual passive smectics,
Okay.
columnars, all that. Yeah. Yeah, all of this is well sorted in, if you are interested, in long articles by Tom Lubensky, and also most of it is in Chaikin Lubensky. So yeah.
Oh, okay.
Yeah.
Yeah, I've looked at that book, but I don't recall this discussion. So maybe I just forgot. Well, thanks anyway.
Thank you.
Maybe to clarify, maybe the question I think was perhaps more about the static correlation functions, right? Because for dynamic
Okay.
correlation functions, you
Yeah,
need
yeah.
Yes. Then you need, yeah. Then you need,
hydrodynamics, but for
yeah.
static, you don't. That's just completely
Yeah.
described
For
by
sure.
energetics.
Yeah.
And smectics don't have in even in 3D, they have quasi long range order, right?
Yes. Yes.
And columnar phases are they better?
That's 2.5 for them. But yeah.
Okay.
Yeah.
They're also quasi long range.
Yeah.
Okay. Okay. Other questions? All right. If not, I will stop the recording over here.